So in this video I want to explain the sorting algorithm called Shellsort. It's a variation of insertion sort, and actually I would say it's a smarter one. The reason why it's smarter is because there's one observation for insertion sort. Whenever there is a comparison or an exchange, it is always a comparison or exchange between neighbors. So if you have an element that is very far away from its final destination, now then it has to make a lot of steps to reach this final destination. So it would be smarter to achieve or to build something, a variation of insertion sort where elements get faster to its final destination by doing comparisons between elements which have a larger distance than one. So that's the rough idea of Shellsort. So it is a variation that does the comparisons with elements always with the distance h, and this h is obviously always greater than 1. And the only thing is that this value of h varies, and it is just decreasing from values that are suggested by some experiments. And as long as the final value of h is 1, it will always be correct. So so if h has reached its minimum 1, what the whole algorithm boils down to an insertion sort and will be ensure correctness. So if you look at the source code over here, you see that these two inner loops here are pretty much the same as as insertion sort. The only difference is that instead of 1, you always find an h here. So this is the value of the distance between the elements that we compare or exchange. Yeah? So this ensures that we have larger steps as long as h has a large value. So on here you see there is a sequence of h values in this static array here, and it is not clear whether this is the perfect or optimal selection. So there are many open questions for Shellsort. Yeah. So this is one suggestion that works quite nice, and you see if you look at these h values, they are roughly so this is a factor of 3, this is a factor of 2 dot something, and this is a factor again of 2 dot something. Yeah, so they are decreasing, not by halving or something like this, but by some intermediate value between 2 or 3. Yeah, but as long as we have 1 as final value, we always know, okay, it will be correct, because if h has finally the value 1, we know it boils down to an insertion sort. Now let's see how it works. So we make a single step, and what we see is here an array of size 20. So initially it will set k to 0, starting with the first distance. Yeah, so now h has this increment value, so it's roughly 1 million something. Yeah, and I is set to the same value, and as long as I is and now these two inner loops start, and as long as I is less than n, it does something. Well, now I has this h value, so 1 million something. So this is clearly larger than 20. So nothing will happen in this loop. And we increase the k, so now we try to do the same stuff with 400 something or 400,000 something, and we do nothing. So the first time we will do something will be when h gets the value of 7. So we make a number of steps. So now we got it. What has happened now? K has the position has reached this position of h values. So now I has the value of 7, and you see that something happened in the simulation. So some values are shaded and some values aren't. So actually with age being 7, we have 3 elements that we look at. So this is the element number 0, so this is 7, and this is 14. And as I mentioned that this works like insertion sort, this simply means we now do the same job as insertion sort does, but only looking at these 3 elements. So now we do this while loop, we make a step, and so we set j to the same value as I is, so a and j are equal now. We compare, we check whether j is greater or equal than h. This boils down to the question, does it have a predecessor that has the distance h? Yeah, in this case we have 7. So since it has, we do the comparison. So this is the symbol for comparison here. And if it's in the wrong order, we make an exchange. Yes, it's the wrong order, so we do the exchange. So now we exchange these values, and what has happened is that this element, they made a swap, and they made a swap with a distance of 7 steps. So this, in case of insertion sort, this would require 7 exchanges and 7 comparisons, right? So the minimal values and the maximal values make larger steps towards the right direction. Yeah, and so this was the first comparisons. Now we decrease the j, and we check whether it has a predecessor. No, it hasn't, because it is the initial part. So I is increased by 1. So now the curtains are shifted by 1 step. So now we have 3 elements that we consider again, but they are different now. But they have this distance of 7. And we do this check again. Does this element have a predecessor? Yes, it has. So we do a comparison. Okay, they are in the right order. We do nothing. Yeah, and then we shift the curtain again. And now we do the comparison between these 2 elements here. So they're in the right order. We do nothing. We shift the curtain. So now we compare these 2 elements here, this one and that one, and they are in the wrong order. We swap. Yeah, so this element has made a step of size 7 towards the right direction. So that's the way why that's the reason why Shellsort typically is faster than insertion sort. So now we shift the curtain, we do the comparison, and we swap because they are in the wrong order. We shift the curtain, right order, we shift the curtain, wrong order, exchange, we shift the curtain. Okay, right order, we do nothing, we shift the curtain, and we make an exchange because this was the wrong order, and now we proceed. Yeah, so this has the correct order, nothing happens. This is nice, correct order, nothing happens. So this is the wrong order. This element, these 2 elements are in the wrong order, so we make a comparison here now. So we do the swap. Here we are. And what happens next is that we consider this one. Yeah, so this inner loop proceeds here, and since this has yet another predecessor now, so this element was exchanged here, but it has yet another predecessor with distance 7. So we do the compare between these 2 elements here. And now they are in the right order, everything is fine. We stop this inner loop and shift the curtain. Then we do the same analysis with this element. We will compare with this one, we will swap, then we will compare with that one, and we will swap too. So this will be swapped twice. So let's see, compare, swap, compare, swap. Yeah, and then there's no predecessor within this array, and so we proceed. We swap the curtain. Yeah. However, there's no need to swap the curtain anymore because I has reached the end of the array. You see, and so as a consequence, we now increase the k. So we now change the curtain size. So when we make the next step, the curtain size changes to a distance of 3. So a completely different set of comparisons now. Yeah, so things with elements which have been compared with a distance of 7 are now intermixed, so to say, with the elements which have the distance of 3 or 6 or 9 and so on. So now we make a completely different set of comparisons now. Yeah, but nevertheless, the elements which are small are shifted towards the to the beginning of the array. And elements which are large are shifted to the end of the array, but now with a smaller distance of 3 now. So we make smaller steps, but still we make larger steps than insertion sort. So we make a swap here, we do the comparison here, okay, we swap it, and so on. We shift the curtain, now we make a comparison, nothing to do. Now we shift the curtain, do the comparison, nothing to do. We shift the curtain, oh, there's something to do, one swap, and we proceed. Again, we make a comparison, nothing to do. We shift the curtain, we make a comparison, okay, something to do. We swap it, then we do the next comparison with the next predecessor. Okay, this is the correct order, we don't do anything now. We shift the curtain. So, right order, nothing to do, shift the curtain. Right order, nothing to do, shift the curtain. Wrong order, do the exchange. Next predecessor, okay, still wrong order, do the exchange. Now it has the right order, stop comparing and shift the curtain. And so on. So now you see how it works. I speed up a little bit. So now I has reached the end of the array. And so since I has reached the end of the array, we increase the k, we proceed with the next increment and with the next h value, and this happens to be 1, so there's no curtain anymore. So now we did, the algorithm boils down to a plain insertion sort. But you see what the outcome of these early loop or early iterations of this outer loop is. It is roughly sorted. It's not perfectly sorted, but it's roughly sorted. And then insertion sort does not have to do that many steps anymore. So if we do the insertion sort now, you see there are only few steps for the majority of elements. Yeah, because they are roughly close to their final position. So that's the way why this Shellsort happens to be faster than insertion sort in practice. Yeah, it's still not the best algorithm on this planet, but it's at least acceptable. Yeah. So now it's finished. Okay.